Something remarkable happened in Chile on June 23, 2025, and at first, it barely received the attention it deserved. High above the Atacama Desert, a brand new observatory was beginning its first serious tests. The Vera C. Rubin Observatory had not even entered its full scientific mission yet, but during its early observations, it was already revealing thousands of objects that had never been identified before. And this was only the beginning. Located on Cerro Pachón, the observatory sits in one of the darkest and driest regions on Earth, making it an ideal location for studying the night sky. The project took decades to develop, and at its center is one of the most powerful astronomical cameras ever constructed. The LSST camera contains roughly 3.2 billion pixels. To understand how enormous that is, a typical smartphone camera has only a tiny fraction of that capability. The Rubin camera is so large that it is comparable in size to a small vehicle, and each exposure can cover an enormous section of the sky. In a single image, Rubin can observe an area many times wider than the apparent size of the full moon. But the real power of Rubin isn't simply taking beautiful pictures. Its purpose is to repeatedly photograph the sky and compare those images over time. That allows scientists to detect objects moving through space, stars suddenly changing brightness, distant explosions, and other events that might otherwise remain invisible. The observatory is named after Vera Rubin, the astronomer whose work helped transform our understanding of the universe. For decades, Rubin studied how galaxies rotate. What she discovered created a major problem for physics. The outer regions of galaxies were moving much faster than scientists expected. Based only on the visible material inside those galaxies, gravity should not have been strong enough to hold everything together. Something else had to be there. Something invisible. That mysterious material became known as dark matter. We cannot see it directly, but its gravitational influence appears to shape galaxies and large structures throughout the universe. And decades later, the observatory carrying Vera Rubin's name is now designed to investigate exactly these kinds of cosmic mysteries. During its early testing period, Rubin produced an astonishing result. In only a small amount of observation time, astronomers identified thousands of previously unknown objects within our solar system. The discoveries included asteroids in the main belt, objects traveling far beyond Neptune, and several near-Earth objects. What makes this even more impressive is that these observations happened before the observatory had officially begun its full survey. Scientists expect the numbers to become dramatically larger once Rubin operates continuously. Over its planned decade-long mission, the observatory is expected to identify millions of asteroids and other small bodies. Among them could be objects that pass relatively close to Earth, helping astronomers build a much more complete picture of the population surrounding our planet. But one discovery from Rubin's early data was particularly strange. Astronomers found an asteroid designated 2025 meganewtons 45. It is hundreds of meters across, yet it appears to rotate incredibly quickly. Its rotation period is only around 2 minutes. That is extraordinarily fast for an object of its size. Many large asteroids are thought to be loosely assembled collections of rock and debris, often described as rubble piles. Because gravity is the main force holding these objects together, there is a limit to how quickly they can rotate before their material begins separating. Yet this asteroid appears to rotate far faster than such a structure should allow. That raises an important question. What exactly is holding it together? One possibility is that the asteroid is much more structurally solid than typical rubble pile objects. Another possibility is that it could be a surviving fragment of a much larger body that was shattered during the violent early history of the solar system. Either way, an object like this can provide scientists with clues about how asteroids formed and evolved billions of years ago. But the asteroid wasn't the only extraordinary discovery connected to Rubin's early observations. There was another object that came from much farther away. Something that did not originate in our solar system at all. In 2025, astronomers announced the discovery of an interstellar object known as 3I Atlas. It became only the third confirmed visitor ever detected traveling through our solar system from another star system. The first such visitor was discovered in 2017. A second was identified a couple of years later. Each discovery completely changed the way scientists think about objects moving between planetary systems. And then astronomers looked back through Rubin's early observations. They discovered that the observatory had already photographed the interstellar visitor before its official announcement. Rubin had captured multiple images of the object while it was moving through the sky, allowing scientists to study its motion and surrounding material. Think about what that means. An object formed around another star, somewhere else in the most difficult mysteries in the universe are often the ones we cannot see directly. Everything around us, stars, planets, galaxies, and even the atoms that make up our own bodies, represents only a small portion of what the universe contains. The overwhelming majority remains unexplained. One major piece of that mystery is dark matter. Scientists cannot simply point a telescope toward dark matter and photograph it. It does not produce or reflect light in the way ordinary matter does. Instead, researchers detect its presence through gravity. Its influence can be seen in the way galaxies move and in the enormous structures connecting galaxies across the universe. The Vera C. Rubin Observatory is designed to study these effects on an enormous scale. Over the course of its survey, Rubin will repeatedly observe billions of galaxies. By measuring their positions, shapes, and changes over time, scientists can build an increasingly detailed map of the universe. One particularly important technique is called weak gravitational lensing. Light traveling toward Earth can be slightly distorted when it passes through regions containing large amounts of mass. Because dark matter contributes to that mass, those tiny distortions can reveal where invisible matter is concentrated. It is almost like trying to locate an invisible object by watching the shadow it creates. The more galaxies Rubin observes, the more detailed this cosmic map can become. And that could help scientists answer one of the biggest questions in physics. What is dark matter actually made of? For decades, researchers have proposed different possibilities, but direct detection has remained extremely difficult. Rubin cannot simply capture a dark matter particle in a photograph. Instead, it can study the enormous gravitational fingerprints dark matter leaves across space. But dark matter is only half of the mystery. There is another component of the universe that is even harder to understand. Dark energy. In the late 1990s, astronomers discovered something unexpected. The universe isn't merely expanding. Its expansion is accelerating. Something appears to be driving this acceleration. Scientists call that unknown influence dark energy. We know very little about its true nature. It cannot be photographed directly, and researchers mainly study it through its effect on the expansion and structure of the universe. This is where Rubin's massive survey becomes especially important. By observing galaxies across huge distances and studying how cosmic structures developed over time, scientists can test different explanations for dark energy. Perhaps it remains constant. Perhaps it changes. Or perhaps our current understanding of gravity and cosmology is incomplete. Rubin's observations could help distinguish between these possibilities. And while dark matter and dark energy represent the long-term scientific goals, the observatory is also designed to detect events happening much closer to home. Rubin continuously watches the sky for changes. An asteroid may appear in one image and move slightly in the next. A star may suddenly become brighter. A distant stellar explosion may create a new point of light. A previously unknown object could enter the field of view. The system is built around identifying these changes automatically and sending alerts to scientists so they can investigate them quickly. That capability became obvious when Rubin's early alert system began producing an enormous number of detections. The observatory can identify changes across the sky at a scale that previous surveys could not easily match. Among the phenomena scientists hope to investigate are supernovae, variable stars, active galaxies, and objects moving through our solar system. One particularly fascinating target is something known as a failed supernova. Normally, when a very massive star reaches the end of its life, it can undergo a spectacular explosion. But theoretical models suggest that some massive stars may follow a different path. Instead of producing a powerful explosion, the star could collapse directly under its own gravity and form a black hole. If that happens, there may be no enormous explosion announcing what occurred. The star could simply disappear from view. Scientists have searched for evidence of this process, but confirming such an event is extremely difficult. You need to observe the same region of the sky repeatedly and notice when a star that was previously visible suddenly vanishes. That is exactly the kind of problem Rubin is built to investigate. Its repeated observations create a massive time-based record of the sky. Instead of seeing the universe as a collection of still photographs, astronomers can begin treating it like an enormous cosmic movie. Every new frame provides another opportunity to discover something unexpected. And that may ultimately be Rubin's greatest strength. It isn't focused on observing only one object. It is watching enormous portions of the sky again and again. That means scientists don't have to know exactly where the next discovery will happen. The telescope can find it first and ask questions afterward. Over its long-term mission, Rubin is expected to dramatically increase the number of known objects in our solar